All right, so we're talking about it's called the difference between means, okay, and or doing hypothesis testing on difference between means. But what it allows us to do, like I said earlier, was if we have a particular treatment that we want to see if it has an effect on an outcome, we will maybe take a group and let them be our control group, take a second group, let them be our treatment group, and then we can look at results, okay? Maybe we're looking at mean blood pressure levels or something like that based off of blood pressure medicine and see if there's an impact collectively on the mean. It says this process is for when testing independent means in known population standard deviation. So we're going to know sigma, okay? So if you remember from anything that we've done so far, if we know sigma, then this is going to utilize the Z distribution, okay? Says two samples are independent if the sample selected from one population is not related to the sample selected from the second population, okay? So we're looking at two populations here, all right? Maybe we're looking at males compared to females. Maybe we're looking at seniors compared to sophomores or something like that, where you cannot have one individual in both groups, okay? Or we, as a researcher, maybe as a medical researcher, we say these people are only getting the placebo, these people are only getting the actual medication, and they're not going to cross over, okay? So it says two samples are independent if the sample selected from one population is not related to the sample selected from the second population. It says two samples are dependent if each member of one sample corresponds to a member of the other sample, okay? So it says dependent samples are also called paired samples or matched samples, and those are things that we are not going to deal with in this section, okay? So what we have to do ultimately in the future is identify, do we have dependent or independent samples, okay? So here are some examples of independent and dependent samples, or matched or paired samples, and I think you'll see why they call them matched or paired here in a moment. But here it says sample 1 is going to be the weight of 65 college students before their freshman year, okay? Sample 2 then is weight of the same 65 college students after their freshman year, okay? So you weigh them, and then you see at the end of their freshman year, you weigh them again and see if there was a difference, okay? Because each individual can be paired or matched to themselves, essentially, in these two samples, this would be called a dependent sample, okay? Or we could match them or pair them. Does that make sense? Okay. If we go down to the next one, it says scores of 38 adult males on a psychological screening test for attention deficit hyperactivity disorder, ADHD. It says sample 2 scores of 50 adult females on a psychological screening, okay, for the same thing. Now, in this, you can see that the sample sizes are different, right? 138, 150, okay? That in itself might be able to tell you that these are not matched or paired, okay? Because there's not a one-to-one correlation, right? In the first example, we saw 65 and then 65. So each one could be paired back to themselves or a one-to-one. In addition, we've got the idea that the males cannot be in the females and the females cannot be in the males, okay? So they're independent samples here, okay? So there's no way to create a pairing between the two samples. Sample sizes are different. The next one says systolic blood pressure of 30 adult females, systolic blood pressure of 30 adult males, okay? Same idea here. Now that's 30 and 30, so it could be dependent, but we got to think about the population, okay? And we see that different people in the two populations, female in one population, male in one population, you can't match or pair them, okay? But you might be able to see, this is the type of stuff that we do in, like, if you have instructors that take your data before you ever take pre-testing courses, Okay, take pre-test and then take the post-test, and then if it's done correctly, a lot of times the pre-test should be these same questions that the post-test has, so that they you can kind of what we say standardize the results. So let's say I gave you a midterm, and I considered that my pre-test. Okay, final exam of the same 14 students, call it the post-test. If we look at those, okay, because of these 14 students paired then with these 14 students, they're the same group of people, right? Does that make sense? Okay, so that's a dependent, so the pairing can be created between the two samples. What a lot of times teachers will do, now I'm not sure that because, just the demographics of your teachers and their exposure to using statistics in a meaningful way, you might get a pre-test, and then they might get the post-test, okay, and they might look at the two and say, oh, we did better. But they probably don't run through the hypothesis testing to say, yes, we did better. Does that make sense? Okay. But they do this type of thing to see if the practices that they employed during that period of time between the pre-test and post-test were productive. Okay. Were they impactful? Were they meaningful? Or would you have done, if you did worse? Okay. Maybe we can see that the practices were detrimental. Okay. So there are things that we can, and we'll call it the treatment, essentially. We can see if the treatment had a bearing on the outcome. Okay, so that's kind of what we're getting into today. Here's the athlete's performance before and after a training program. I like to look at when I do weightlifting with baseball players, back when I did it with football players, I would take the data and I would see, okay, did the things, we got stronger, but is it a significant strength increase? And we could do the hypothesis testing on the data to see whether the program that we instituted was impactful. Okay. So in that situation, you would have dependent samples. Here it says students' performance on a pretest compared with student performance on a summative test. So student performance on a standardized test for sophomores in 2019. So this one here, that's going to be dependent. Okay, you can match them. Student performance on a standardized test for sophomores in 2019 compared to performance on a standardized test for sophomores in 2020. Is that a independent or dependent scenario there? Can you be a sophomore? Now, theoretically you can, okay? But like are this year's sophomores, are they going to be the same group of people as next year's sophomores? No, right? And that's what this is saying, okay? So I'm going to look at basically the end-of-course exams for this year's students compared to next year's students, compared to maybe the next year's students. And what we can do there is see, and that's what the state does when we get those grade cards about your school. Basically, they're taking the data from this year and data from last year and comparing was their growth with those students. All right, so key concepts here says if the sample sizes are large enough, so central limit theory says N has to be greater than or equal to 30. And if you don't have greater than or equal to 30, as long as they say the population has a normal distribution, if your samples are independent, then the sampling distribution of the difference between sample means, that's what that is, x bar 1 minus x bar 2, that's the difference of sample means, is a normal distribution with the mean and standard deviation as follows. Okay. Now we talked about this back in I think it was like section 9.4. Okay. No, sorry, 8.4. About where these things come from. Okay. But that is the mean. The mean obviously is going to be the difference. Okay. Says mu sub x bar minus, or x bar 1 minus x bar 2 is equal to mu of x1 minus mu of x2. We can break those apart like that. Okay, so you see this is different notation than that, which basically then says is the same thing as the population mean of population 1 minus the population mean of population 2. Standard error, okay, our sigma sub x bar 1 minus x bar 2 is found by using this formula here. Okay? But this formula looks a little bit different, but that formula is still your observed means, and that's x bar 1 minus x bar 2, minus your expected means, the difference of your expected means, divided by your standard error. That's the same structure for our z-test that we've done, for our t-test that we've done, all the hypothesis testing that we've done so far. That structure there is what will standardize our data to allow us to make decisions, in this case, on the difference of means. Does that kind of make sense? All right. If that's beyond you, we can still at least run through the formulas, put things in our normal curve with rejection regions or p-values, and still make decisions if we don't necessarily maybe understand where the formulas come from and why they are what they are. Okay. So suppose a researcher wants to determine whether there is a difference in the average age of nursing majors at a community college compared to the average of nursing majors at a university. Okay, so the researcher is not interested in the average age of all nursing majors. They are interested in comparing the means of the two groups. Okay, so it's a research question. It says, does the mean age of nursing students who enroll in a community college differ from the mean age of nursing students who enroll at a university? Okay. You know, a lot of times when we get situations like this, we're looking at maybe community college versus university. A lot of community college, like nursing majors, are maybe people that didn't go to college right away. Okay, maybe they started a family, now they've got their family underway, and now they go back to school, right? So a lot of times, and when I teach out at Rhodes is a community college, when I teach out there at night, I've got a lot of adults in my classes. Okay, so if I compare that to a university, usually universities those are the 19, 20, 21-year-old people that know what they want to do. They go right into it. So maybe their ages are different. Does that make sense? Okay. So that's what this research question is trying to get at. Now, not interested in saying that, which one's more, which one's less, or how much are they different by, that kind of thing. We're just looking right now to see, are they different? Okay. So we always, I think this is important. We could use different subscripts to make this more informative or more obvious, but I use mu1 and mu2. And then I think it's important somewhere to remind yourself, well, what is mu1? Mu1, I've identified it there, defined it as the mean age of all nursing majors at community college. Okay? If you want to make it more obvious, maybe you say that is mu sub C for community college. And then the other one may be mu sub U for university. Does that make sense? So you can see or remind yourself which one's which. Okay? So those subscripts are identifiers, so you can make them what makes sense to you. Okay? When we do this, okay, we're always going to write our null hypothesis, the expected value, to be equal. We assume that they are the same. Okay? The populations are the same. And then the hypotheses will allow us to either reject that. If I reject that they are the same, that would mean that they are different, right? Or we would fail to reject that they are the same, which would then result in them being the same. Okay? So that's what we're looking for. Are they different? So this is what we accept. Okay? First say, no, they're not. That's our null hypothesis. We need data then to show us that they may be different. Okay? So then the alternative hypothesis is the complement of that. Okay? Does that make sense to everybody? Now, you may see alternative ways of that being written, okay, because we could do some subtraction on both these. Subtract mu sub 2 over, because that's what we're doing. We're doing hypothesis means on the difference. So maybe some people will like to see the difference written in the null hypothesis, okay? If their difference is 0, then that means they were the same number, right? Does that make sense? Okay. And the alternative hypothesis, I don't know why this didn't, I might have cut and pasted this and then not went back and fixed the equal sign. But this, in the alternative hypothesis, this should be a not equal to sign. Just put a slash there. So you might see either one of those represented. I like to look at this one, okay, but there's nothing wrong with using this one. Yes?
I'm not sure if you said it, sorry, but like, why does U1 like the same for both the policy?
Oh, that's another problem. That should be a 2. Good catch. Okay, so a lot of times I'll cut and paste things, and because it's a pain in the butt to use the when I'm on Word, using the equation editor on Word, it's a nightmare. So I'll cut and paste things I've already put in, and I just didn't change that one. It's my fault. Thank you. All right. No, nothing. These two things say the exact same thing. This is the idea that we're directly saying population 1 and population 2 are the same, or the average of population 1 and average of population 2 are the same. Here, saying that they're not the same. Okay. Here, this null hypothesis is an alternative way of looking at that null hypothesis, just because we subtracted mu sub 2 from both sides, right? And if I have two averages, when I subtract them, I get 0. That means my two averages were the same, right? Does that make sense? Which is the same thing that this is saying here. Says if there is no difference, then subtraction will obviously yield 0. That's what we talked about. Says if there is a difference, then subtraction will yield a positive or negative value. Okay? So the nature of this number will allow you to decide how they are different. Okay? It will allow you to show or determine whether mu1 was greater or mu1 was less than mu2. Okay? So the theory behind testing the difference between two means is based on selecting pairs of samples and comparing the means of the pairs. Okay? So all possible pairs of samples are taken from the populations. The means of each pair of samples are computed and then subtracted, and the differences are plotted. Okay? So the means, says if both populations have the same mean, then most of the differences will be 0. Does that make sense? Okay. Obviously, if they're not the same, if populations are not the same, then most of the means will not be 0. Okay. So occasionally there will be a few large differences due to chance. Okay. Some positive, some negative. If this is all plotted, these differences will have a mean of 0 shaped like a normal distribution. Okay, so that's kind of the logic of why we use a z distribution here. Okay, because if the populations are the same, most things are going to subtract to give you 0, which is our mean on our standard normal curve, and then you're going to have some, because of chance, because I could pair value A with value B, and they might be completely different just by chance, but you're going to get a few of those. Okay, so if I plot all that stuff on a curve, it will be a normal curve. Okay, says rejected or not rejected can be decided the same way as previous tests using critical values and or p-values. And then this is our first example. Okay, so a lot of this stuff they will initially give you, especially in Math Excel, when we see some assignments in there, they will give you the breakdown of the data like this. Okay. Here it says a credit card watchdog group claims that there's a difference in the mean credit card debts of households in New York and Texas. So the results of a random survey of 250 households from each state are shown. It says, do the results support the group's claim? Okay. So can you have credit card debt as a person in New York and then be the same person living in Texas? Is that possible? Can you live in New York and Texas at the same time? No. Okay. Now you might have properties in New York and Texas, but you're not living in them both at the same time, and you don't have debt from them both at the same time. So these are, what we're getting at here is that they're independent, okay? Our sample sizes are large, okay? And if we go through here, says note, because both samples are large, sample standard deviations can replace population standard deviations. So our formula, we want to use sigma in our formulas, but if we don't have that, as long as our populations are big enough, our samples are big enough, we can replace sigma with the sample standard deviation. Okay, so all we're going to do is take these formulas here, and we're going to standardize our data and see if there is a difference. So first thing I want to do, though, is write my null hypotheses and my alternative hypotheses. So the first thing is H sub 0. Okay. Now, it doesn't matter the way that you do this. Okay. I'm going to say mu, and I'm just going to put subscript of n for New York, is equal to mu subscript Texas. Okay, if you would have written it differently, you could have gone New York, or Texas on the left and New York on the right, correct? Would it still tell me the same thing? Yes. Okay. So my alternative hypothesis then will be mu sub n does not equal mu sub t. Okay. Well, you're going to see it written maybe this way as well. So they'll say mu sub n minus mu sub t. So just subtract that mu sub t over, and that would give me 0. Correct. Correct. So we see it written that way. Because then people ask me, well, how do I know that you go New York minus Texas? Well, it doesn't matter. Okay. Because it's still going to be a two-tailed test. I could go, or it could be mu of Texas minus mu of New York equals 0, and mu of Texas minus mu of New York not equals 0. Does that make sense? Okay. So you've got options there. Like I said, I prefer to use this one, but you might see, maybe view an example or help me solve this or something like that in Math Excel, they might use that notation. Okay. All right, so now what we want to do is we want to look at this information and decide how to compute our z value. Okay, so we're going to compute our z value. So we'll take x bar 1 minus x bar 2. So I'll take these two numbers and I'll find their difference. Okay, now I'm going to go, if you just pay attention, I'm going to go New York minus Texas. Okay, and that shouldn't be I'm just trying to keep that pattern. If I have to use that pattern over throughout the course of the problem, I'm going to go New York minus Texas. So 4446.25 minus 4567.24. Okay, so my differences here, that is that number right there, ends up being negative 120.99. Okay, minus, now this is where it's important to understand where this value comes from, and it's from, previous examples, previous concepts have always helped us with this. Maybe this p-value, when we did proportions, okay, that always came from the null hypothesis, didn't it? Okay, when we did here and we found this mu value, look at this, mu is 40 in this case. If we compare those two things right there, where did that 40 come from? It came from the null hypothesis, right? If we look at this, we need mu1 minus mu2. We need a value for that. Well, if you think about our null hypothesis, we're saying mu1 and mu2 are the same. So if mu1 and mu2 are the same, or mu-n and mu-t are the same, what is their difference? 0. This will always, in the difference, the hypothesis testing of difference of means, that mu1 minus mu2 will always be 0. Okay, we're going to run out of time here. So tomorrow we'll pick up with this. All we've got to do is plug in the information from up here in that denominator, calculate, and then plot. We have to determine an alpha value that we want to look at, but we can plot and decide whether to reject or not reject.